Good morning, and thank you for joining our webinar. I remind you that the webinar is recorded and all attendees are muted. In case of any questions, please do not hesitate to raise your hand, and I will contact you privately for any issue with audio or any other setting. If you have questions regarding the topic of today's webinar, please use the Q&A box on the bottom right side of your screen. Thank you, and enjoy the webinar.
Hello and welcome everybody to the third part of our webinar. My name is Peter Balzer. I'm an application specialist for our joining systems. I will start today with a short presentation to show you the topics for today. Today we are talking about our evaluation objects. Here you see a list of all our evaluation objects. We have 23 overall different types of evaluation objects, and I will guide you through all types to show you the function and features for each and every one. So here just a small list of our available evaluation objects. So afterwards, I also would like to show you our advanced configuration. For example, how you can set up an evaluation object, for example, in UNI-BOX, just to have it like a dynamic window. Also, I would like to show you the hysteresis function and also the meaning of the catch zone. So before we start our live session, I would like to give you a short overview about the general types of our evaluation objects. So it begins with a no pass. No pass is a special threshold. It's special because it has an additional digital output. This means you can define a so-called no-go area for the curve. If the curve is hitting this threshold, an output for the PLC will be generated, and the PLC has the possibility to stop the process immediately to avoid any damages on the tool, on the parts, and so on. The next type is the most often used type. It's the so-called UNI-BOX. With the UNI-BOX, you can freely decide the entry and exit sites. It also don't need an exit site. You can also use it as a final window to, for example, just check your block force or your maximum displacement value. You can freely decide the entry and exit site, and you can also use it as a no-go box with no entry and no exit. I will give you for each of these evaluation objects later some examples. The next one, or the next both, are also thresholds. This is a threshold X and a threshold Y. It simply checks the force or the position at a specific area of the curve quite easy. Also, the next one is the envelope. Envelope can also be used for the forward and backward direction. You can also enable a trend adjustment for the envelope. I will explain this later. The next one is a quite good evaluation object. It's often used. It's called getRef. You can get some reference points of your curves. For example, a maximum force value, the maximum displacement value. You can also grab a gradient change. For example, if the spindle enters a hard mechanical block, you can grab your reference points and use it, for example, as a reference for a threshold or for the UNI-BOX. The next type is a so-called calculation element. With a calculation element, you can calculate two different variables. For example, you can calculate the point where you have touched the part and calculate the distance till you have reached the final block position, for example. The next evaluation object is a speed window. Like the name already says, you can check the joining speed in a specific area. The next two is the so-called gradient evaluation object. Gradient, here for example, gradient Y, gives you the information about the gradient changes inside of a specific area of the curve. It's available in Y and also in X direction. The next both evaluation objects are so-called hysteresis evaluation objects. So if you are measuring the forward and backward direction of a joining process, you can define a maximum deviation of the displacement value for the forward and backward curve. And also with the Y evaluation object, you can also define a maximum force variation for the forward and backward. The next one is more or less the same like in UNI-BOX, but with additional no-go areas. And this tunnel box has also the advantage that it also can generate an live output. So, for example, if you're using a tunnel box for the first touching of the part and it exceeds the force, you can directly stop the system without any impact from the PLC. So the maXYmos NC itself can directly stop the joining process if you enable the online evaluation. This is not possible with an UNI-BOX. That's something special for the tunnel box only. The next one is the type, is the type time. Here you can measure the time in a specific displacement area so you can calculate or you can see how long it took to cover a distance of, let's say, 20 millimeters, for example. The next one is the so-called average window. The setup is more or less the same like in UNI-BOX, but it doesn't give you numbers for the maximum force value or the minimum force value like in UNI-BOX. It will give you the output of the average force inside of the window. So even if you have a small peak out of the area of the window, it doesn't force to be NOK if the average value is still okay. That's the difference to the UNI-BOX. Okay, the last page. Here we have a break window. Break window detects, for example, if you are using a tool which can be break or which is broken during the process, you will have a curve like this. The force is constantly rising and then it drops down to zero. For example, your tool is broken, or for example, something is broken inside of the part. So you have a significant change of the gradient, and this can be evaluated with the break window. The opposite is the so-called inflection window. With the inflection window, you can also calculate an immediate gradient change. For example, this is used to cover or to make sure that you have reached the hard mechanical block. For example, if you shaft if you press a bearing onto a shaft or something, and you need to reach the block position. Some specific window is the so-called integral window. It covers the area, or it evaluates the area below the curve, and this window can give you the work as a measurement value. Another one is the so-called digital in window. With this digital in window, you can check if in between a specific displacement area and digital input was set or not. You can check edge, a rising edge, or a constant level. The next one is the so-called delta Y evaluation object. Delta Y is more or less the same like the hysteresis window, with the difference hysteresis covers only one point, and with the delta Y you can cover a whole area. So for example, like in this case here, you can check on which position here you got the maximum force deviation between the forward and backward curve. And the last evaluation object is the so-called trapezoid evaluation object. It's more or less the same like in UNI-BOX, but with an UNI-BOX you have only 4 set points. With the trapezoid window you can use up to 6 set points. So you can arrange it like this for the trapezoid Y, or like this with the trapezoid X. Okay, now I'm finished with a small presentation. I just want to give you a short overview about the evaluation objects generally. And now I'm going back, like always, to my live session and show you the functions live via VNC. Okay. So I've prepared a few different programs. Let's have a look at this. So first of all, I just want to show you each and every one of these evaluation objects. So we're starting with the no pass, just like in the presentation now, and I will also give you some information about the UNI-BOX regarding the advanced configuration. Okay, let's start with the first program. In this program, I just have set it up in so-called no pass threshold. So if you're entering the evaluation screen, you see here, first of all, you can choose your evaluation objects. We can set up to 10 different evaluation objects. And with this drop-down screen here, you can choose the type of evaluation object. So it starts with a no pass and continues with the other one I just showed you. So one is no pass. I will enhance the display or the zoom functions. And here you see this no pass threshold. I'm using here to cover the whole idle stroke. So we are starting at 0 millimeter and the force starts to rise at about 76 millimeter or something. So I'm covering the whole range with this no pass threshold. And if the curve is touching this threshold, it will be automatically marked as NOK, and a live output will be generated. So I set it up 2 different programs for it. So the first one, I'm starting right now. So with the first program, everything is fine. The curve is not touching the threshold and will be marked as OK. So with the second program, you will see I just changed the position of this threshold, and now the curve is touching the threshold and it will be automatically marked as NOK. It's just the same like a normal threshold with one exception. If we are going into the field bus information to the output bits, you will see on the output side that there's a special output for this threshold, which is called no pass. And this one is active as soon as the threshold is touched. So with this information, the PLC can directly stop the joining process to avoid any damages on the machine or anything else. So that's quite an easy threshold, often used to avoid some damages on the machine. Again, OK, and the NOK cycle where an output will be generated. If the PLC doesn't use this information like I'm doing it right now, the joining process will be finished as normal, but it will be marked automatically as NOK. Okay, that's the no pass. The next one I would like to show you are the single thresholds. It's the so-called line X and line Y. So here, for example, we have the line X. We can go into the setup. It's quite easy, only 3 set points. So here you can choose the area for displacement where it should be placed, and here your force level, and the crossing below for forward measurement and above from a backward measurement, for example, if you're having a pull measurement or something. This threshold delivers you only 2 values, or more or less only 1 value. You can grab the result and the entry value as a measurement value. So if we are going back to the actual process value table, you will see the value here. So it's quite easy threshold. The next is the line Y. I also created a program for this one to check, for example, the force at this position. The setup is more or less the same, but in this case you have 2 set points for the force and 1 set point for the displacement, and the values are also the same. You get 1 result if it was generally OK or NOK, and for example, in this case, the force at this position, 179 Newton in this case. So this is quite easy. So now I would like to continue first Unibox setup. So now here you see more or less all possible configurations for the Unibox. The first one here is a so-called no-go Unibox. This means the curve is not allowed to touch this area here. So no entry and no exit. The first Unibox has the entry from below and the exit to the right. The second one, entry from the left, exit to the right. The third one, entry from left, exit above. And the fourth one, entry from below, exit from above. And the last one here is only entry from below without any exit. So this is more or less all configurations what you can do with an Unibox. Let's have a look into the setup. So it looks like this. You have generally always 4 set points. You have your minimum and maximum displacement value. You got your minimum and maximum force value, and you can choose freely your entry side. So this can be no entry, left, right. You see the list here. All what is also possible any. So the entry can come from any side. If it's from below, if it's from the left or from above, it doesn't matter. No influence on the result in this case. And also the same for the exit side. So now let's have a look at the advanced configuration. So first of all, you can say involved in total result and statistics. So if you unmark this checkbox, I would like to show you what is happening. So I've created another measuring program for this. So now exactly same setup in the measuring program, but now you see, excuse me, this was the wrong program. This one I would like to show. So first here we have a normal NOK result. So you see we exceeded the maximum force. So this is NOK, nothing special. But now if we have the same curve with this checkbox deactivated, you see the overall result is okay, even if this window is not okay. And this is happening when you are unchecked this checkbox involved in total result or not. Why is this function available? For example, oh, this was the wrong one. This was UNI-BOX number 5. And here I've just unchecked the checkbox involved in total result and statistics. So this function is useful if you want to place an evaluation object just to grab some values. If it should not be involved, if it's a good or bad part, just if you want to information, for example, in this area, what is the maximum force, what is the maximum displacement value, and so on, you can use an evaluation object, unmark this checkbox, and then it has no influence in the total result and also for the statistics. So this is just a possibility which is available for the of the evaluation objects. So the next thing is the curve part. I want to skip this. I want to explain this one later, but you can imagine here you can say if you have a forward and backward measurement, you can choose for which measurement this evaluation object should be used for. For example, the positive, so the forward movement, or the backward movement, or in this case, I don't care. It could be any part of the curve. So now I would like to go first. Also, I would like to skip this one. First, what I would like to show you is the so-called hysteresis. Hysteresis, here you have a graph. So hysteresis in x direction means you normally exceeding, or you just have an additional, how can I say, an additional value for your entry in this case. So let's go back. So here, for example, we have 800 Newton up to 850 Newton. If I would set up an hysteresis of 100 Newton, it could go down to 700 Newton, and it could go up to 900 Newton in this case. So if this hysteresis is just a possibility to enhance your entry or also the exit limits of your evaluation objects. The same for hysteresis X. I have an example for this one. So for example, now have a look at this curve, and now I'm driving the same cycle with some hysteresis active, and now you see we are exceeding the limit here, but the total result is still okay. So let's have a look at a setup. That's because I set it up on hysteresis of 100 Newton for the evaluation object number 5. And even if we are exceeding, like you saw it in the example, exceeding the total limit of 850 Newton, but with this additional 100 Newton, the curve can even end at 950 Newton. So this is just a possibility to enhance your maximum limits of the evaluation objects. It's a little bit tricky because you need to go into advanced settings and choose the graph here to show what is going on. Because if you see something like this in your production, you will ask yourself, how can this be? And just for information, there is a hysteresis function available. Normally, I do not recommend to use it because it's really confusing sometimes. You need to check each evaluation object if it's available or if it's active or not. But I just would like to show you that this possibility is available to use hysteresis for X and Y side. Okay, the next thing I would like to show you is the so-called catch zone. So the standard settings for each evaluation object is always unlimited catch zone. So what does this catch zone mean? So here you see evaluation objects, in this example, entry from the left, exit from above. So normally, if you have a curve like this, you won't get any measurement values because the curve is not hitting or is not fitting the area of the evaluation object. If you have a catch zone with 0%, you won't get any value. You will get, for example, if you are checking the maximum force inside of these evaluation objects, you will get none as result. None means no measurement value available because the curve hasn't touched the area of the evaluation objects. If you set it to unlimited, and you are checking, for example, the maximum force of this for this evaluation object, and also, for example, the maximum displacement value, you will get these values instead. So this one will be shown as maximum force. It will be marked as NOK for sure. But if you need to have a value, for example, because you are forwarding this, you are exporting CSV files or XML files, and you need a value because you are creating a database or something, you need any measurement value. None is not acceptable for SQL or something. This is why we enabled this function. So I can show you the difference. So more or less the same curve like we had it already. The first one is with unlimited catch zone. So the curve stops before we are reaching the window. If we are going to the process value table, you see there are still values 940 Newton, even if we do not touching the area of the evaluation object. So now exactly the same program with 0 catch zone. And now you see no value because we haven't touched the area of the window. So the standard settings is unlimited. You can also, you saw it in the drop bar, you can also set it to 15% or 50% or whatever. But generally, I would recommend to use always unlimited, because then you will receive any time, in any case, in value. It will be marked as NOK for sure, but you will receive a value, and this can avoid any problems with forward processing for this for measuring values. For example, if you are using it to create a database or something, you need a value. None is not acceptable in this case. So this is the unlimited catch zone. So I just saw I skipped the hysteresis X function. I also have created a program for this. So you saw already the hysteresis function for the y-axis, and this is also available for the x-axis. So here, for example, this evaluation objects now I attached with an hysteresis of 1 millimeter. So if you see something like this, you see normally the entry side is from the left and no exit, but it is still okay because let's have a look at the setup again. I enabled an hysteresis of 1 millimeter for this evaluation object. So hysteresis 1 millimeter, and then it's still marked as okay. So please, if you are using the hysteresis function, tell it everyone who's working with the machine, because this can lead to a lot of confusion. The best way is not to use it, or only in some specific applications. Okay. So the next thing I would like to explain you is the reference X and Y function. So normally it's absolute. Absolute means it's reference to the 0 point of the axis of the joining module. But there are two possibilities, trigger Y and block. So what does this mean? I also would like to show you something. I've created another program for this. So imagine a configuration like this. I'm sorry, this was also the wrong program. I can show this one first. Here is the explanation for the forward and backward direction. So here, let's go into the setup. Now here you see the forward curve, and here now backward curve. And you see the forward evaluation objects are always marked as orange and the backwards as blue. And now if we go into advanced configuration, this is what I showed you before. It's curve part positive, it's always marked as orange. And the second one is only for the backward curve, it's marked as blue. So this one first. But now we are coming to the reference. I'm sorry, but I've created so many programs, lost nearly the overview. So, but now this is for the reference function. So now you see this one, or this side of the evaluation objects are reference to the block function. Now let's have a look at the setup. So it's normal UNI-BOX entry from the left side, exit to the right side. So nothing special till now. But if you have a look at the advanced configuration, now the reference X changed from absolute to block. Block means, now you see it here in the diagram, always the last measurement value for the X-axis is used as a reference for these entry and exit sides. That's why you are seeing here negative values. For example, now the 0 point or the block point is now 0 millimeter, exactly 0 millimeter. And now the exit side of the window is now referenced minus 0.5 millimeter back from the block position. And the entry side of the evaluation object now is referenced minus 1.5 millimeter back from the entry side. So now, if we are driving a few cycles, you won't see any changes because it's more or less the same. Okay, only small changes because the rubber is a little bit moving, but now I just want to lay some pieces of papers in between. So now I try it again with a few pieces of paper below, and now you see the window is automatically moving depending on the block point. Now a few pieces of papers more. And this can, for example, simulate some tolerances from the parts, from the tool holder or whatever. So now you see the window is moving depending position of the block. Again, without any papers, back to the original curve. So that's a so-called dynamic UNI-BOX. If you are using reference X as block and set up your entry and exit side with some minus values, then you have exactly this configuration. So what is it used for? For example, imagine you have a curve like this. When you use the standard application, you want to press a bearing into a shaft or something, onto a block position. And now the most important process value in this case is not a block force, because it can be pressed on block. You will always reach, for example, in this case, 900 Newton or something. The most important process value in this case is the holding force just before you reach. And this is exactly what you can grab with this window. Now, of course, it's just an example. We can move this side a little bit nearer to the block point, but generally you can use this exit value. I think here, for example, the exit value now is 212 Newton. This is the force value at this position. If I would move this exit side of the window a little bit nearer to the block position, I would grab exactly the holding force of my bearing in this case, which is used quite often, for example, in the gearbox assembly. So again, just with one piece of paper, again, to simulate some tolerances of the machine. And now you see, you will always grab the holding force. So that's a quite useful function. Okay, another example could also be dynamic force values. So another example. Now, let's have a look at the setup first. that you understand what I have chosen here. So if you go to evaluation, so here we have our UNI-BOX, advanced configuration. And now you see in this program, I've chosen the reference for the y-axis, or for the force in this case, to block. And now here you have negative force values. This means the maximum side of the evaluation object now is 142 Newton, and the minimum side is minus 153. So it's also referenced to block to the last measured force value in this case. And now we can do exactly the same like before. Now I can use a few pieces of paper. Now the force in this area will be a little bit higher, and now you see also the window is moving, but now it's moving in the y direction again. So another cycle with a little bit more paper. Okay, this was a little bit too much. Now just remove one and try it again. Okay, now it looks better. And now the next program is a combination of both. So you can also choose. So now in this next program, I have chosen for the X and the Y axis reference as block. You see it also here marked X and Y. And now again with a few pieces of paper, hopefully not too much this time. Now you will see the evaluation object moving in X and Y direction. That's it. That's a dynamic window, or let's say a dynamic UNI-BOX. Reference to block position. There's another possibility. You can not only use the block position, you can also use in trigger Y. I would like to show you the curve first. I need to remove the papers. So now I've referenced it to trigger Y in the next program. So now you see trigger Y means a threshold, a force threshold in between of the curve. Let's have a look at the setup. Measuring program setup. Measuring program number 16. Evaluation. It's the UNI-BOX, like always. Advanced configuration. And now you see reference for the x-axis is trigger Y. And trigger Y you can set up in the next screen. It's this one. And here you can choose a threshold. For example, 50 Newton. You can go down to 25 Newton. For example, any force you are touching the part, you can choose a trigger in value X at trigger Y, for example. And now I set it up 78 millimeter. It's more or less the same like it would display absolute. But you can also choose, for example, 10 millimeters. And with the trigger Y, here it would display 10 millimeters as position. Or you can also choose 0 to generate a complete new 0 point when you have touched your part. Everything is possible. But now I am keeping my setup because I don't want to change too much. I just want to show you the function. Here you can set up a trigger Y threshold. There is also a possibility which I not use too often, but the possibility is given. For example, here you can reference your whole graph to block or trigger Y. So this means the whole graph, not only single evaluation objects, will be referenced to block or trigger Y. This is also possible, but I'm avoiding to work like this because it has some disadvantages. For example, if I would set up here a new 0 point, I have some differences to my sequence editor because here I see, okay, at this position, my spindle is moved 78 millimeters. Now, if I reference it back to 0, I always need to keep in mind my position. The sequence editor is still 78 millimeters, but here 0 is displayed. So this is sometimes a little bit confusing. This is why I like to work with the absolute values also for the evaluation. What's also possible, block don't need to be 0 millimeter. You can also display 100 millimeter. And now if I would reference my evaluation object here to block, you see it on the set points. Now it's 98.5 and 99.5 because now the device will display at block position exactly 100 millimeter. You can use this if you need to fit some values from the drawings or something. Then you can work with reference on block and choose any value from your drawings to use value at X. But in this case, it's 78 millimeter. Sorry, the 0. I'm not working with block here. I'm back to trigger Y. So now I also need to change the reference again, back to trigger Y. Okay, so now it's referenced to 50 Newton. This is quite useful if you want to reference your evaluation object when the part is touched, even if you have, for example, some high tolerances on the part itself, from the part holder, from the tools, whatever. If you need to cover some high tolerances, you can always use this threshold, and then for each part, the beginning, or let's say the part after the touching force, will be exactly the same. Then maybe it's useful to use it really dynamic on the trigger Y, the whole graph referenced on trigger Y. Then it can be useful if you need to cover some real big tolerances. But in this case, I just want to show you the function. So now you know the setup. Again, another cycle. So now again, a few pieces of paper. So one more cycle, then you see the force is changing and the window is also, the evaluation object is also changing. So this can be used to cover some tolerances from the part itself. Okay. So that's more or less the UNI-BOX explained and also the advanced configuration. So now I would like to continue with another evaluation object, the so-called envelope. So another program. Oh, I need to remove the papers. Okay. So now another program with the envelope. Now envelope is explained quite easy. If you don't want to use UNI-BOX or trapezoid windows later, you can choose this envelope. The setup is quite easy. Let's have a look at it. So the precondition to use the envelope is always the envelope cannot set it up like this. For example, it doesn't work like this. An envelope needs always an entry side and an exit side. It's not allowed that a curve is finished or is ending inside of the envelope. So the curve always needs to go out of the envelope. So for example, like this. And then it's working. You can choose your entry side. It depends on if you want to measure your forward direction or backward direction. And we have 4 different functions and 2 different algorithms. First one is tolerance Y. Tolerance Y means if you set up, for example, 50 Newton, each measuring point, you see it here, will have a tolerance with plus minus 50 Newton. If you choose tolerance band, it will be something like an average value. So you see the entry and exit side changes a little bit. So now you won't see any changes, but if you would like to cover only a few measuring points, like we have it on this block position, tolerance Y is working, tolerance band is not working because the average value doesn't work in this case. So that's why we also developed 2 algorithms. I will always recommend to use the tolerance Y function. For the offset, or let's say for the maximum deviation, we have 4 different types. Constant symmetric, so we have plus minus 50 Newton. Asymmetric means you can choose an upper limit of 20 Newton and a lower limit, for example, of 10 Newton. And then it's getting a little bit complicated if we are talking about a standard deviation. So it's something special. If you need it, you can choose it. Okay, so this is the most used function with the same deviation for plus and minus. And there's something special about the envelope. There's the so-called trend tracking. So if I enable the trend tracking, you can, for example, choose each or after each, let's say 5 curves, I want to adjust my limit values. So here you can choose your trend width, for example, 100 Newton, and warning at 50%. So this means now, after each 5 cycles, if the trend of the envelope is going up, for example, it's going constantly up over 5 or 10 Newton, you can automatically recalculate your upper limit up to this value, in this case 100 Newton, and you will get a warning if the actual upper limit was it did it up to 50 Newton, in this case 50% of 100 Newton. So this can be used for really fast cycles, which are in the most cases not happening with the maXYmos NC. I always would like to recommend it. It can be useful for some applications, but if you don't need it, I would deactivate it. And then you know, okay, my limits are here. I have 25 Newton of this reference curve. And if I need to change it, I can change it manually without any automatical recalculation. As I already said, for some application, it could make sense, but in the most cases, for me, I would avoid to use it. I would change, if needed, I would change the limit on my own. Okay, that's the envelope. Another measuring program for another evaluation object. Now we are coming to the getRef evaluation object. So if you have a look at a curve like this, so I'm always using the same sequence. It doesn't make sense to talk about the sequence. There's one exception with the inflection window, but you know the sequence. If you have a look at part 1 and part 2, it's always the same sequence. So I just want to focus on evaluation object at this time. So here we are going on block, and here we have two getRef windows and one normal UNI-BOX. So here you see some purple crosshairs. Here you see this is the first getRef window. With this getRef window, I'm just grabbing the displacement value when the part is touched, or in this case, the rubber of the demo unit is touched. With the second window, I'm calculating my inflection point, or the gradient change, when I'm going forward to the block position. And the UNI-BOX here is referenced to the displacement value of the block position. The displacement value of the block position. So now, before I'm entering the setup, I would just like to repeat the test with the papers. So now again, a cycle with a few papers. And now you see also this window is moving depending on again without any papers. Looks like this. Okay, so now let's have a look at the setup. Like always, measuring, choose your measuring program set, then evaluation. And here you see the getRef. Entry site you can choose, or you can choose also any. It doesn't matter in this case. Choose your entry site. It needs to be fit, otherwise it will be marked as NOK. But you can also set it up like this, any, so it doesn't matter if it's the right entry or exit site. But in this case, I've choose this one. Entry from below and exit to the right. So now here you also have your 4 set points, like always, like with the UNI-BOX, and here you can choose your function. For example, xmin means I'm just grabbing this entry value when the part is touched. I could also grab the entry force when the is touched, or I can also use the entry side. I can use exit if I want to have this point, or I can also use the inflection point, which I'm using with this window. So there is a lot of possibilities, or I could also use the average force inside of the window. So there are a lot of possibilities. I just want to show you the most common used one. So here, for example, I can grab the displacement value when the part is touched. With the second evaluation object, I can grab the bending point. This means I grab this point when we are reaching the hard mechanical block. So for example, here bending position, that's this function. Here I need to choose in delta x. Delta x means inside of the evaluation objects now every 0.05 millimeter, it will the device is looking if the bending is in between the minimum and the maximum bending. So more or less if the minimum bending was exceeded. If the minimum bending was exceeded, the inflection point is detected. So now you see the upper limit, the upper maximum limit is 100,000. That's a real big value. It never can be reached, but it's important that the value is in between minimum and max. That's why I have chosen this big maximum bending value and the small one here. And the good thing is there's always, if you load a reference curve via a history buffer, there's always the bending value shown. For example, here it's nearly 4,000. So now I have chosen 1,000. It's more or less 1,000 Newton per millimeter. So that's a hard mechanical block. And now this Unibox, the reference is now, you see there's not only trigger Y and block available. If you're working with getRef windows, you can create your own reference point for these evaluation objects. So for example, I could reference it to Xmin for when the part is touched, or I can reference it to the bending position from the reference window too. So both is possible. So that's great. That's really an amazing evaluation object because you can create a lot of reference points which can be useful, especially in combination with the calc element, which is the next one I would like to explain. So again, now here we are grabbing, let's have a look at the process value table. Okay, I just have chosen the okay result, but we can change this one. If we go to measuring program setup, program 18, let's have a look at the process value table. And here, for example, we can always choose reference X and reference Y. For the second one also, that's the window we are grabbing the inflection point. Yeah, the UNI-BOX is not important in this case. So now with this setup, let's try another cycle. Now here you can see the position of getRef window 1 is 77.65 millimeter. Let's check this one. Use the crosshair function. Then we can switch it here. 77.65. Okay, that sounds good. At about 25 Newton. Okay, that's okay. The second one is where the inflection point was detected. It was 80.88 millimeter at 240 Newton. You see it on the crosshair. That's a big advantage of the getRef window. Later on, when we are talking about the inflection window, this purple crosshair is not available. Then you need these two values. But you see, that's pretty good. So now you know, okay, we have touched the part at 70.765 millimeter, and we gone to block at 80.88 millimeter. Okay, so the next one is the calc element. It's more or less the same curve, but with additional calc elements. So here, now for example, this is also an example which I used a lot of times on site during a commissioning. For example, if you want to calculate your real press position. So for example, also if you need to cover some big tolerances, now you know with this calc element, I'm just calculating the point where we have reached the block position and the point where we have touched the part. And the distance in between those two points are 3.23 millimeter. And now the second additional value I'm calculating is the point where we are going to block till we finish the process. So now you see we have a bending of about 0.14 millimeter. That's the calc element. This is just an example. Many more is possible. Let's have a look at the setup. So evaluation. And now here we have our two calc elements. It always works like this. You first of all choose your input number 1. This can be in value from an evaluation object, in our case from a getRef window, but it can also be a general curve value like Mach block X, block Y, and so on. Or, which is new in our latest firmware, it can also be a value which is transmitted by the PLC before the process starts. Any variable, whatever it can be. But it's also possible to calculate variables. Here, for example, reference X, evaluation object number 2, then you can choose the operation, in our case, subtraction, and here we have the evaluation object number 1, the reference X value. And then you can choose your minimum and maximum, and then you can also have an evaluation, or you can also say, should not be involved in the total result. I just want information about the value. So this is also possible with the calc element. It's quite useful for a lot of applications. Okay, so again, another cycle. Or you can also, with an additional calc element, you can also calculate the complete distance. But now I split it up in 2. So here we have 3.23 millimeter and additionally 0.15. And yeah, you can use a third one. Then you know your press distance. So from the beginning, or from the part is touched till the end, you know your part is pressed in this case, 3.38 millimeters, if you combine these two values. Okay, so the next window. So you see, there are a lot of possibilities to do the evaluation. Now the EOS are getting more and more specific. So now we are talking about the gradient window. So there are 2 types available. The first one is the so-called gradient Y and gradient X. This one is the gradient Y. Here you can check your gradient change of the curve. So for example, from this point to the rest of the curve, or to the constantly rising of the force in this area here, we have about 63 Newton per millimeter gradient change. And the same thing is also possible for gradient X. Here you can check, so the value is too low, so it's something like 0.0001 or something. It could not even display this the 4th decimal place, because here we are already in block position. But this can also be evaluated with a gradient window if you want to. And let's have a look at the setup. Evaluation. So the first one is gradient Y. It's quite easy. Just choose your coordinates, and then you can select your entry site. It's also push or pull measurement. Depends on what you are using, and the gradient min, gradient Y, and exactly the same for gradient X. And in this case, it's quite easy, because here you see it automatically changes the value. Everything can be placed graphically, so that's a big advantage. You don't need to calculate anything. Okay, that's the gradient. The next one is a little bit special, because not everyone is measuring the forward and backwards curve. But if you do it like this, the curve will look like this. So what I've done previously, so now we can have a short look at the sequence. What we have done, and for example, with the Line X program, let's have a look at this. So there's one easy change made. Here we are pressing to block, at this case force 800 Newton, and then we are stopping the measurement. So if you want to record your forward and backward direction, you simply need to stop the measurement first when you are back in home position, and then you record everything. So now in this case, here we're going on block, we release, we go back to home position, and then we are stopping the measurement. That's how you can record the forward and the backward curve. And here, if you're using this button here, it will display you the same I showed you previously with the UNI-BOX. The forward one is always marked orange and the backward one is always marked blue. And here we have our turning point. And here you can freely decide with the maXYmos what is your turning point. So now let's go to the global setup. It can be also done on a cycle control from each program, depends on what you want to use. So here we have the cycle control, we have the curve processing, and here you can choose your turning point. So in my case, it's the maximum force. But in some cases, in some applications, especially when the block force is lower than the force, let's say in the middle of the process, then X max X makes sense, because otherwise your turning point will be calculated totally wrong. So, but in my case, it's okay. We can use Y max. And then it's important that you are not cutting your curve, because it would also be possible if I set it up like this, turning point right, I will cut the curve. Let's have a look how it will look like this. So everything is, okay. I'm sorry, this is not working because I'm stopping the measurement only when I'm back in home position. So, no, it should work. I know what's the problem. I have for program number 21, I have my specific cycle control, so it's not used globally. Here. So now if I go to curve processing and do exactly the same, then the curve should be cut. So both is recorded, but then it will be cut. So in this case, this setup is not good. So we just switch off the cutting of the curve. You need turning point left if you have a pull measurement, but for push only turning point right. And if we do it again, the curve won't be cut and we have the same configuration like this. Okay, so this was just an information about the cycle control. So now we have these two hysteresis evaluation objects. So now here we have our forward curve, and this one is the backward curve. And what these hysteresis are doing, they are simply measuring the distance or the difference between the forward and backward curve. In this case, the difference of the force, and in this case, difference of the displacement value. So now you see the difference from forward backward is nearly 0.3 millimeter and about 37.5 Newton. So let's have a look at the setup. So you can choose your position Y with the hysteresis X and your minimum and maximum, and the same for hysteresis Y. So quite easy if you want to see the difference between forward and backward curve. Okay, so now the next one, I need a few more programs to explain it. It's the so-called tunnel box. So there are two tunnel boxes are available. The first one, what you are seeing here, is the tunnel box Y, and this one here is the tunnel box X. Let's have a look at the setup. As I already said during the presentation, the setup is more or less the same like in UNI-BOX. You have your four set points, minimum and maximum displacement value, minimum and maximum force, entry and exit side, but in this case only left or right, push, pull measurement, whatever you are using. And you have one decision you can make, evaluation type offline or online, and I will show you now the difference. The rest is still the same like with a UNI-BOX. So now we already saw this one, and now we have an OK curve. I just moved the tunnel box in this case. Evaluation type in this case is offline, so nothing is happening. The process is still finished, but now we can have a look. While I'm driving in cycle, we can have a look at the output bits. It's not no pass. Now we have online AON OK. And now if I drive in cycle, so now the spindle is moving. Okay, it's not you cannot see it. It goes way too fast. I can only see it from PLC side, but whatever. Let's stop it like this. So now this is evaluation online, and now you see, and now you should see the output. Now you see online AONOK is set it, and now the PLC programmer knows, okay, something is going wrong with the cycle. I can now directly stop it and go back to home position. And now there's nothing needed from PLC side. So the PLC does not have to stop it like with a no pass threshold. Here the maXYmos NC is automatically stopping the process. And then the PLC programmer needs to go back to home position manually. That's what I'm doing right now. So enable the drive, go back to home position, and then you see the process was directly stopped here. That's the Tunnelbox. This function is available for the Tunnelbox X, this online function. I just want to display it, and Tunnelbox Y, I think it's clear. Okay, that's the Tunnelbox with the special output for the PLC. Okay, so the next one is quite easy explained, or the next few ones. So now here we have the speed window, and the speed window, yeah, let's have a look at the setup. So you can place it like in UNI-BOX. You got an entry and exit side like always, and here you can select your minimum and maximum speed. So in this area, since I think in the sequence since 25 millimeter, we are constantly driving with 5 millimeter per second. Then you will see also 5 millimeter as a result. And if you want to make sure that it's working, we can also reduce the speed, and the curve will change a little bit because we do not exceed the force too much, but should not be a problem for the speed window. Let's reduce it down to 2. Okay. A little bit smaller, and you see exactly 2.00 millimeter per second. Now we have not reached the minimum of 4 millimeter per second. That's why it's annual. I think it's clear, it's easy. We can close this one. The next one is also quite easy to explain. It's the so-called time window. So this time window is doing nothing else than measuring the time between the entry and the exit side. So in this case, I've chosen minimum is 0.1 second, 100 millisecond, and maximum is 500 millisecond. And now we needed about 380 milliseconds to go from the entry side to the exit side. And you can place this one on each area of your curve just to measure the time if you want to, because we cannot measure the time when we are measuring force depending on displacement. Then in some cases, this time window can be useful if you want to measure a time. For example, how much time you need to for the joining cycle and so on. You can use this time window if you need to. Okay, the next one is the so-called average window. Let's have a look at this one. So it's more or less the same setup like in UNI-BOX. The only difference is we are not getting a minimum or maximum value inside of this evaluation object. We are just getting an average force value. So the average force value should be somewhere at this threshold. Let's have a look here. A little bit higher, so it should be 160 Newton. So it's more or less constantly rising. So the middle between this one is here. So we have 166 Newton. That looks good. Remember, even if you have a small peak out of the window, for example, from above or something, it doesn't have to be NOK as long as the average value is still in between the limits. This average value is often used with the maXYmos TL with some torque measurements, but for joining systems sometimes, but not too much. I know this average value from a lot of torque applications. Anyway, let's continue with the brake window. Okay, so now we have something like this. What's happening? we have a brake detection available. I need to go manually back in home position, and then I can show you the setup. Okay, so now we have a bending of minus more than 50,000. Brake. What I'm using here just to simulate in brake is I'm just using this Tara element, which I showed you last time in the second part. So here I'm simply taring the force to simulate in brake, and that's the hardest brake you can ever imagine because the force drops directly down to zero. That's why the bending value is too high, so high with more than 50,000. So the setup is more or less like the get ref. The only difference is you can choose a maximum bending. So if the bending which is detected by the maXYmos NC is lower than 1000 or this value here, then nothing is happening. If this bending is exceeded, it doesn't matter if it's plus or minus. So both directions are possible. So if it's less than 1000 Newton, nothing happens. But if a brake is detected, it will directly stop. So it also has a live evaluation output on the PLC side. It's the same output I just showed you with the tunnel box. It's always named as EO evaluation object online NOK. That's one single output from the PLC side, and then the device is automatically also stopping if a brake is detected. And also the same setup like inflection, get ref, it's everything the same. You need to set up a delta X. So every 0.05 millimeter, the device will now search that the maximum bending is higher than this 1000. Regarding this delta X threshold, maybe I will explain this in the details when we are talking about inflection window. That's the next one, but let's keep this set up like this. So we have a maximum bending of 1000. So I just showed you the NOK part, and now the exactly same program, but without any zeroing of the force. It will look like this. So, okay, I forgot to activate the program. I'm sorry. Give me 1 minute.
In the meanwhile, I would like to remind everyone that you can write your questions in the Q&A box on the bottom right side of your screen. Thank you.
Of course, if you have any questions, please let me know. Okay, so now this time with the right program. Brake, okay, without any Tara elements. So you see bending is detected of 224. It's below 1000, so nothing is happening. So you can use this window, for example, or this evaluation object, for example, if you want to make sure that your tool is not broken, your part is not broken, or anything else is happening during the process. Well, you should use it where it makes sense, of course. Okay, so let's come to the inflection window or inflection evaluation object. So that's also quite often used. So program number 30. In this case, it's necessary to that the maXYmos NC is detecting an inflection for the brake. If a brake is detected, automatically marked as NOK, and here it's only marked as OK when an inflection point was detected. So now we have an inflection point detected. Bending is about more than 2000. Let's have a look at the setup. Evaluation. So it's the same like brake, minimum bending, but here we have not max, here we have the minimum bending. So this means the detected bending value should be above or higher than 1000 in this case. If it's lower, it will be marked as NOK because no bending is detected. Also, delta X is always the same here with the demo unit. Every 0.05 millimeter, now the device is checking if the bending, the gradient change is higher than 1000. You need two preconditions that this is working correctly. First of all, if you set up a really low sampling rate like me here with 0.05 millimeter, you need a high sampling rate. A high sampling rate, remember the first part of the training, but I can also explain it again. If you go to cycle control, okay, I'm using the global setup in this case. Then let's use the global. And here you see, now I have a delta X of 0.05 and my sampling rate from the whole process is 0.005, so 10 times higher. That's a good value which you should use, because if you are working here with a sampling rate of 0.2 millimeter, 0.1 millimeter, you can forget to detect any inflection or breaking point. This doesn't work. You need really a high sampling rate. That's the first precondition. And the second one, if you have a really high sampling rate, this all evaluation objects regarding gradient change are quite sensitive. So what's also necessary, or what I would also like to activate every time when I'm using one of these evaluation objects, is a low pass filter. If you're working with 10 kilohertz, you have some small peaks inside of the force curve, or of the display force and displacement curve. Everything will be detected as in gradient change. So please, you don't need to go down to 100 hertz, but at least you should use 500 hertz, just to avoid some small peaks which accidentally can be marked as an inflection point or something. You will mark this quite fast if you have a look at the getref X and Y values, and you know, or you see that the entry of the evaluation object in this case will directly get marked as an inflection point. So if you are using the zoom settings here, now this is a filter with 100 hertz. Now have a look at this. This is quite smooth. But if I would change it down to 10 kilohertz or up to 1 kilohertz, you will have something like this. And this is normal. That's not a problem. It could be some EMC influence or whatever. But this is really the death for the inflection detection, because you never get your inflection detection right detected. That's important. A high sampling rate and, of course, a low pass filter. Otherwise, it doesn't work. So that's my experience. Okay, but if you have a high sampling rate and a low pass filter, this inflection detection is working quite well. Let's have a look at the process. You go into the value table, and here you see the same like getref, or also this also available for the break window, is you can see your coordinates where the bending point was detected, reference X and reference Y. And this is what you should check if you're using it. Because unfortunately, maybe they will do it in newer firmware versions. Like in the getref window, a small purple crosshair would be really good in this case. It's not available to now. Maybe it will change in the future, hopefully, but we can also check it manually. So if we have a look at the process value table, you see the bending point now, or an inflection point in this case, was now detected at 80.83 millimeter and 333 Newton. Now let's use the crosshair function. 80.83 should be somewhere in this area. Now we have 80.88. Okay, so now you can be sure the right inflection point was detected, because if it displays with a wrong setup somewhere here, you know, okay, any small peak from the first signal was detected accidentally as a bending point, and then this will never work. Okay, so now I have a standard setup here. Here you see condition. We have talked about this in the last part. We have position, force feedback, and there is something new which we can use now. It's the inflection detection. This is what I have activated in the next program. And now what is happening? We are not stopping at 800 Newton. We are directly stopping when the inflection point was detected. So now let's have a look how this looks like. So it looks like this. So now again, let's check first. Okay, this looks good. 80.83 millimeter bending point was detected, and we stopped at 80.90. So we exceeded 0.07 millimeters. That's okay, because if you want to calculate a bending point, you need 3 points. The first one, the bending point, and one afterwards. And then the device is exceeding always a little bit. But remember, it's 0.07 millimeter exceeded from the bending point. So the zoom here is just looking quite big, but it's only 0.07 millimeter. Okay, now this is one possibility. And now what a lot of people are doing, they using this inflection detection, but they want to make sure that they have 100% on the hard mechanical block. So there are two possibilities which is used quite often. So the first one is you can additionally detect your inflection point and add, for example, 0.1 millimeter additionally. So let's have a look at the sequence. Inflection. So now I simply added a new motion. So here, still the same like before, inflection detection, then an additional motion block, so relative from the position where the inflection point was detected, 0.1 millimeter with slow speed because we are already on block, and then stopped. Then you know, okay, from the inflection point, I additionally added 0.1 millimeter to make sure that everything is fine. What is used quite more often is the same thing, but only depending on force. So here we have the same. Let's have a look at the sequence. So we are already entered the second page of the measuring programs. So here we have the same setup, but we have relative up to 0.5 millimeter, and the condition is force. So, and one thing, it's not absolute, it's relative from below. This means with the previous motion, the inflection point gets detected, and with this additional motion, we are just adding 300 Newton up to it. And then we can be sure, okay, from the inflection point, we simply added 300 Newton, can be also 10 kilonewton with bigger spindles, doesn't matter, but yeah, that's the way how you can do it. And how it's really oftenly done. Okay, that's the inflection detection. Important two things, high sampling rate and of course a low pass filter to avoid any spikes, and then it's working quite good. Okay, so now let's continue. A few evaluation objects are missing, only 4, but let's continue to keeping time. So the next one is the so-called, it's quite special. I used it only one time. One customer wanted to have the mechanical work, and this is what this window is doing. It's calculating from the curve, so the area below the curve, and with this area you can calculate the mechanical work. It's 422 joule in this case. That's what the integral is doing. Let's have a look at the setup. So it's quite special. We implemented it especially for one customer, for one big customer, which has the requirement for it. So you can choose your coordinates, minimum and maximum, and then you can calculate your mechanical work. Okay, so the next one is digital in. Digital in is also explained quite easy. So here you have an area. Your coordinates is minimum displacement, maximum displacement, where digital input should be activated. So let's have a look at the setup. So only 2 are missing after this one, so we finish quite soon. So digital in, here you can first of all choose your digital input. So only real digital input, so 24 volts are possible field bus. You can choose, do you want to detect in rising edge or in constantly level through this area, high or low. So let's take this one. It's easier for me because I need to activate my switch. So now let's have a look at service. And here you see the digital I/O status. You see the last one was marked and okay. So now I'm just turning my switch, and then this input goes on. So okay, and now we can do the same cycle again. And it should be marked as okay because the necessary input is set. That's it. And here you see there's a mark. Okay, it was directly set from the beginning. If you're using the function edge, then in this area somewhere should be a rising or falling edge detected from the digital input. So both is possible. Setup. let's go to digital in, evaluation, and here you see it's, like I said, only two coordinates, the area, minimum and maximum, and then you can choose your level from the signal. Okay, so one more with the forward and backward measurement. That's the so-called delta Y evaluation object. That's the next one. So now we are already recording, or we again recording the forward and backward curve. And now this delta Y evaluation object is detecting the biggest deviation or biggest difference between the forward and backward curve in this area. So in this area, it's this one here. Here we have up to 31 Newton difference between the forward and backward curve. It's more or less like hysteresis Y, but remember hysteresis Y is only detecting it at one point, and here we can cover a whole area of the curve. So that's the difference. Let's have a look at the setup. Delta Y evaluation, and here you see coordinates and the maximum, in this case 50 Newton from my side. You can also go a little bit lower, then it can go up to 37 Newton. Okay, so now the last program and also the last evaluation objects I would like to explain, that's the so-called trapezoid window. It's more or less the same like in UNI-BOX. The only difference is you got 6 set points. Depends on which one you are using, X or Y. You can have 4 set points for the X-axis or 4 set points for the Y-axis. And here I have also chosen the function. Remember, orange one is for the forward direction and the blue one is for the backward direction. Let's have a look at the setup. Whoop. Evaluation. And here you see, for the Y, you got 4 set points. So one point is this one, the lower one, and the upper one. And this side also with 2 values. Yep, and the same for trapezoid X, but here you have 4 force values. Sorry. Okay. I'm sorry. Both are trapezoid Y. I was just confused. Yeah, trapezoid X would look like this. And yeah, unfortunately, I haven't found a way to set it up right because it can look like this. So if you need an evaluation object which is looking like this, you can set it up here, for example. Yeah, we can also place it. It doesn't make sense, but it would be possible. Okay, let's set it up like this. I don't know if it's useful, but for this application not, but maybe for some other applications. But trapezoid Y, of course, is quite useful for a lot of things. If you don't want to use an envelope for any reason, then you can do the curve shape like this. Okay, so that was everything. All evaluation objects explained with different programs. Now we have reached trapezoid Y, and now, yeah, after 1.5 hours, I'm finished now. And now I would like to go to the question and answers part. If you have any questions, please let me know.
Okay, thank you very much, Peter. So we have one question that is, can envelope be deactivated for total results? How can we store a history curve in evaluation window?
Let's have a look at the envelope. Here we are. So the envelope cannot. Sure. It was in the previous version. It was not available, but here, yes, you can deactivate the if it's depending for the total result or not. This can be deactivated, also for the envelope. And how we store a history evaluation window? That's quite easy. there are two options. So first of all, I'm deleting everything. So now if you want to get an reference curve inside of the evaluation window, you have a few possibilities. The first one is you start in cycle automatically. So you just need to push begin capturing, and then you can start in cycle from the PLC side. I do it right now. So it's measuring program number 17 for me. Let's start this one. And now everything will be directly captured here. So that's one possibility. The other one is you can also do it manually. The problem is in my sequence, I'm automatically setting the auto bit. This is not good in this case. It doesn't work. Maybe it works in manual mode. Manual. So start. Okay, now my PLC sequence is not working correctly. Yeah, that's a problem. That's a problem from my PLC program. So I'm just showing because now the feedback signals are missing in this mode. But generally, it would work if you're working with an auto process. Auto bit is set. Just a moment. Oh, to reset my PLC sequence. Okay, so I'm sorry, but this is a problem from my PLC program. But generally, you can use this one. But it's more often used is the history buffer. So if you have already pressed in some parts and you have some curves available, or even if you have a pen drive which are already stored some curves CSV, for example, from another device, you can also load this one. But the most often used one is history. So if you pressed some parts like we did it previously, you can select your measuring program. In this case, it's the active one. It's measuring program number 17. And here we have the last curves. So let's use this one, for example. Import curves. You can choose only the last one. And then this curve is implemented into this evaluation screen. Okay, now we have only, that's the wrong one. Oh. Okay, we imported this one. So let's use this one. Then you can go to extras. Copy curve to filter. Yeah. Now you can have the curve number 1. Okay. And now this curve should be imported. Okay, now it's working. Okay. So that's the way how you get a reference curve into the evaluation screen. The easiest way if you go through the history buffer. Okay, break evaluation again, of course. So the break evaluation is measuring program 28. This was the NOK. Do we have any specific questions regarding the break detection or anything else?
So I don't see any more questions. In case you have any more questions regarding today's webinar, please do not hesitate to contact me or my colleague or my colleagues. My email address is valentina.zucchelli@kistler.com or giuseppe.lamacchia@kistler.com, and we will answer you as soon as possible.
So there's, Valentina, sorry, but there is one open question regarding the break window. I just want to finish this
Oh,
one.
yes.
Okay. So how does the break evaluation is working? So break detection is working like this. Here you can set up the break evaluation window. let's go to the sequence again. Need to drive back in home position first. So, and now the device is just checking if inside of the window, let's go back here. Just a moment. Okay. Yeah, now it's working again. Okay, so now we have the brake detection here, the brake window. You can set up your coordinates, so in this area, for example. Then you can, then you need to first of all choose your delta x. This means every 0.05 millimeter in this example, now the device will check if the gradient changes more than 1000. If the gradient changes is bigger than 1000, the device is detecting a brake. This means here you only have a minimum a negative bending if the curve is going down or something is breaking. So this window is doing it, and now if the brake or if the device is detecting and bending bigger than 1000, it will automatically detect and brake and will automatically stop the spindle. That's how it works. Again, so now brake is detected. Now I can go back to home position. And if no brake is detected, like in the next program, it works correctly. Okay, that's it.
Any more questions, anyone? Okay. So again, if you have any more questions, please not hesitate to contact us. Recording will be available and published on our website. Please do not hesitate to subscribe to our newsletter for receiving more invitations to the following webinar. And we will receive more information regarding webinars next week, which is scheduled for Tuesday next week. At same hour, so from 1 p.m. to around 2:30 p.m. more or less. Thank you for participating, and have a nice day.
Thank you and have a nice day.
I said thank you and have a nice day. Hopefully see you next time. Goodbye.